Well, hello again, everybody. We are here to continue with our coverage of the probability sections. Next section we will cover is section 7.2, which is, let's call this probability part 2. Okay. So last time in section 7.1 we mentioned some definitions. Keep those in mind. We will use those in the future. So let's begin this section by discussing the counting formula. So the counting formula begins in this form. So this lowercase n is not being multiplied by anything. This is just a variable. This whole thing is a variable. It's just has one value. So NA plus NB minus NA intersection B. So last time we talked about the union and the intersection sets. We said that union is everything in A and B included, or another way of thinking about it is everything in A or everything in B or everything in both. But the intersection refers to just the common set. And these are the counts of elements in each set. So this would be the count of elements in set A. This would be the count of elements in set B, and in addition to what we've already discussed. So let's look at an example of how we can use this formula. So we want to find the count in the union set, or n of A union B, given that the count in set A is 14, the count in set B is 11, and the count in set A intersection B is 6. Okay, so remembering that formula, we just plug in. This is just an example to warm up to what this formula can do, or is asking us to do in this question. So the count of elements in A union B is equal to n, the number of counts of elements in A, which is 14, plus the count of elements in set B, which is 11, minus the count of elements that are common to both sets A and B, so minus 6. So here we have 25 minus 6, or 19 in A union B. Okay, here we subtract the intersection because the elements that are common to A and B, when we add these two sets, if they have common elements, those elements will be double counted, right? Because they're common. There are elements of the same kind here and here as well. In order to subtract the double counting or eliminate the double counting, we subtract the intersection piece or the common elements only once. Okay, so that's the reason for that. All right, so let's see another example of that shows us how to apply this counting formula. So suppose are taking history or mathematics. Okay, so let's apply the counting formula, but first let's attach notation or symbols to these quantities that we have, right? We have 4 of them. So suppose that out of 1,500 first-year students at a certain college, 350 are taking history. So let's call that number of people who are taking history are 350. And those who are taking mathematics are 300. So number of those taking mathematics are 300. And 270 are taking both history and mathematics. So that would translate into an intersection event or set, right? History and mathematics. So that would be 270 people. So how many first-year students are taking history or mathematics? So this phrase or, history or mathematics, translates into the union symbol. So this history or mathematics is under the question. Let me add quickly, in statistics and probability, whenever you read this or that, it's implied that it's history or mathematics or both. So even though there is no phrase or both, that is part of the notational interpretation of history or mathematics. So it's implied, it's not explicit. That's why we take history and or mathematics, or history or mathematics or both. Okay, so or both is part of this phrase, this or that, in statistics. So quickly, if you assign symbols to this, you can see that this is really an application of the counting formula. So let's add. So we know that this is equal to the number of people who are taking the history course, the number of people who are taking the mathematics course, minus the number of those who are taking history and mathematics. Again, this subtraction is because when we add 2 sets that have common elements, and in this case we do have, the sets do have 270 people who are taking both history and math. So those 270 people are part of this piece and part of this piece. When we add them, we're double counting those 270 individuals. So in order to eliminate that, we subtract that once, and it gets rid of the double counting of individuals in this problem. Okay, so then we have 350 plus 300 minus, of course, the 270, and so we end up with 380 who are taking either history or mathematics or both. And again, the or both piece of this is implied. It's not explicitly part of the problem statement. Okay, so now let's consider this as part A of this problem. Part B, we would like to draw the Venn diagram for this scenario. So let's do that. Okay, so let's call part B for us to draw the Venn diagram. Okay, so we have 2 subjects that are being taken up by these students. So let's say that we have, let's call this the mathematics, and there are individuals who are taking both classes, so then let's make that history, and let's take this, the sample space. So this box represents all 1,500 individuals. Okay, so when you're asked to draw a Venn diagram, always start with the junction part first. Sometimes you have more than one junction. You will see that maybe in today's lecture, I think. You always start with the innermost junction piece of the Venn diagram. In this case, we just have one junction between the two sets, right? These are the individuals who are taking history and mathematics. So, starting with this, we have 270, right? So I'm starting from the junction part. 270 who are taking both history and mathematics. Then we were told on the previous slide that the total number of people who are taking history was, so N of history was 350, number of those who are taking math was 300. Okay, so if 350 are taking history and 270 of them are here, then we must have only 80 people, right, that are taking just history, not mathematics. So 80 should be out here. That's why I say we always start from the innermost junction of a Venn diagram and work our way outward toward what numbers or probabilities should be placed in each of these regions. So 270 plus 80 is 350. And these 250 because they're taking history and mathematics. By the same token, to find out how many people we should have here, it should be subtracted from 300. So 270 are taking math and history, and we have total 300 people who are taking mathematics. So 30 people should be in this region. These are people who are just taking math. Okay, all right. So the question then is, how many people should be way out here? All right. Well, the total number of students that was surveyed for this data had 1,500 people in it. So 1,500 minus all of these added, minus 30 plus 270 plus 80, that would be equal to, let's see what I have, 1,120 people. So that 1,120 people would be placed in this part of this Venn diagram. So what do these people represent, right? These people represent those, and that's all of this space outside of both circles. So all of that region includes this 1120. Those who are not taking history or math. Okay. And then, so these people are taking only math, right? Taking only math. And these people are taking only history. And of course, that junction part is where 270 are taking both. Okay. So let's see an example with three different categories. Okay. All right, suppose we have 100 college students and they were surveyed So they were surveyed about visiting 3 cities, and these cities were Austin, Texas, Boston, Massachusetts, and Chicago, Illinois. Okay, and so here is the data. We have 53 who visited Austin. We have 52 who visited Boston. 65 visited Chicago. And then let's put the rest of data on this side. We have 19 who visited Austin and Boston, and we have 28 who visited Boston and Chicago, and we have 31 who visited Austin and Chicago, and we have, at the very bottom, we have 38 who visited exactly one of the cities. One of the cities. Okay. So the first part of this problem is, let's call it A. Draw the Venn diagram, or the whole thing actually, not part A, but the whole thing is draw the Venn diagram for this data. Well, this is not a question mark, sorry. So this is cities, just a full stop. The question is, draw the Venn diagram for this. Okay, so there are 3 cities that are being visited by these students, and so we must have 3 categories, 1 set for each of the cities, and 38 visited exactly one of the cities. So there is no one out of these 100 college students who didn't visit at least one of these, right? So let's draw the Venn diagram. Maybe I can move this up a little bit. Like that. And then another one here. And then another one right here, right? So in this case, I'm not going to put a box around this because there's no one would be outside in that box. So let's take this one as those who visited Austin, and then as Boston, and then finally those who visited Chicago. Okay, so what we learned from the previous example was that always start from the junction piece of the Venn diagram and work your way out, right? And so in this case, when you look at this data, you scroll it down, when you look at this data, it doesn't say how many visited all 3 cities, right? And of course, that would be in this region right here. So we need that. We need to know if we're to have any numbers here at all, we need to know how many visited all 3 cities. And it's not been given to us. So it's a critical piece of information, so let's call it X, as anything else that we we have in mathematics that is unknown, we assign a variable to it. So let's assign a variable to the unknown number in this Venn diagram. Then the other junction parts come next. So this was the innermost junction piece, and which we didn't know. The next pieces are this region, this region, this region, before we put any numbers on the in the outside of this overlapping regions, right? The overlapping regions are where we want to start first. Okay, so we do have some numbers for those. So I'll start with, it doesn't matter if we start with Austin, Boston, or Austin, Chicago, but I'll just work my way up from here. So 31 visited Austin and Chicago, right? So that means that the, let's see, let's start Austin and Chicago, this one. So if we know that, if we knew X, the number of people who would fall into this junction would be 31 minus X, right? So these would be Austin and Chicago, but not Boston, right? And these people would be Austin, Boston, and Chicago. So Austin and Chicago includes everybody here. So if you add X and 31 minus X, you end up with 31, which you should. Okay, for Boston and Chicago, that would be all of this junction area. So that whole thing is 28. If we knew what X was, then the number of people being in this junction, in this part, which would be just Boston and Chicago, would be 28 minus X. Okay, and then finally for Austin and Boston, that would be 19 minus X in this junction here. Okay, so let's work our way back up. Then we have for Chicago, we've been told that 65 people visited Chicago. Okay, so let's calculate what that number should be. We know that it would depend on X because that's affecting everything else. So let's, maybe I can keep everything, not everything, but most of it on the screen. So just Chicago would be 65, right? 65 minus all of that, all of these guys. These guys. So this would be 31 minus X, right? Plus X, plus 28 minus X. All of that, if you subtract all of this from 65, you know how many you have, how many people should be in here. So let's calculate this. So we know that minus X and X add up to 0. And then we have to distribute this negative, right? So we have 65 minus 31, and then minus 28, and then plus X, right? I'm just distributing the minus into whatever I have left because these two cancel each other out. So plus X. And then let's simplify this a little bit. So what do we get? And we get, I ended up with 6, right? 6 plus X. So these are how many people visited just Chicago and nowhere else. Let's write that down here, 6 plus X. Now let's calculate how many visited just Boston, right? So just Boston. That would be, we know that, it's barely visible. So 52 people visited Boston, right? So to figure out how many people just visited just Boston, we have to say 52 minus all of this. So 52 minus bracket 19 minus x plus 28 minus x. Okay, so 52, let's distribute this minus into this whole thing, but let's get rid of these two because they add up to 0. Minus x plus x adds up to 0. So 52 minus 19, let's distribute this minus into everything that is left. Minus 28 minus x is plus x. Okay, so for Boston, we end up with 5 plus x. Okay, after simplifying here. Okay, so then we have to find, well, let me put that 5 plus x where Boston, right here. So this would be 5 plus x. Okay, so we still have to figure out how many visited just Austin and nowhere else. So let's do that here. Just Austin. And this would be, we know that, let me scroll this down so you can see it, 53 visited Austin. That's in total. So to figure out how many visited just Austin, we will do 53 minus all of this, 19 minus x, plus x, plus 31 minus x. So again, the minus x and plus x add up to 0. So let's distribute this minus to everything that's left. So 53 minus 19 minus 31 plus x. So for Austin, we end up with 3 plus x. Okay, so let's write that down here. 3 plus x. Okay, so now that means, looking at this Venn diagram, it's obvious that if we know x, we know everything else in this Venn diagram, right? So let's take advantage of a piece of data that we were given, but we haven't yet used yet. So it's this one. 38 visited exactly one of the cities. Total, right? 38 people. So that means if we add 5 plus 6, plus 3 plus 6, plus 6 plus 6, we need to get 38. So let's do that. All right. So 38 must be equal to those who visited just Austin plus those who visited just Boston, right? These 38 people visited just one city, plus those who visited just Chicago. Okay, so we have the 38, then we have, for Austin, we had 3 plus x, plus just Boston, we had 5 plus x. For just Chicago, we had 6 plus x, right? So let's do the algebra on that, and we end up with 38 equals 14 plus 3x, or x equaling 8. So 8 people out of this 100 visited all 3 cities. Okay, so now that we know x, we can go back and draw our Venn diagram. So let's do that. So here is the 3 circles again. Like that. And we said this was Austin, and this is Boston, and this was Chicago. So I'm just going to say, so that's 8. This was You can't see it, but you should have it in your notes or on the previous slide if you rewind the video. This was 28 minus x, so this should be 20 now. This was 5 plus x, so it's 13. This was 19 minus x, so this should be 11. And this was 3 plus x, so that should be 11 again. And 31 minus x, it was here, so that's 23. 23 right there. And finally out here we had 6 plus x, so that should be 14. Okay, so after we're done, do we get 100? If we've done everything correctly, the summation of all these numbers should add up to 100. So this is 34, 37, 47, 55, and then 58, 78, plus 22, we get 100, right? So this is all works out nicely there. Okay, so this section, this discussion wraps up section 7.2, which was probability concepts part 2. Okay, so let's move to section 7.3, the multiplication principle. This principle is everywhere in probability calculations, and it's called the multiplication principle, and it's got its own section. So that's how important it is. So section 7.3, and this is probability concepts, and for part 3. So counting in general, this is multiplication principle, helps us do many things, figure out probabilities, figure out counts, and so on. But just to show you how important counting random events is in probability calculation, suppose I have pennies in my pocket, and suppose these pennies, the only thing that's different in them is that each of them was minted in a different year, right? So if I reach into my pocket, what's the probability of grabbing any penny that was minted in a particular year? Well, if you were in classroom, and I always get at least 2 people who raise their hand and give the right answer. They say, well, that depends on how many pennies you have, right? So, and that's exactly the correct answer. You can answer the question of what's the probability of getting the penny that, let's say, was minted in 1983 if you don't know how many pennies I have in my pocket. If I have 5 pennies, then the probability is 1 over 5. If I have 10, then it's 1 over 10. If I have 50, that's 1 over 50. So that's the main reason we like to be able to count random outcomes, because the main objective is to calculate the probability, but we need to know the count of events first, and then we can calculate the probability of some desired event out of the total. Okay. So one very useful tool in counting events is called the multiplication principle. So I'll just describe it in words, and then we'll do some examples. That way you know how it works. Sequence of choices. So let me And let's say where there are N1 options. For the first choice, let's say there were N2 options. For the second choice, N3 options for the third choice. And so on, right? And so on. Then can be accomplished in N1, N2, N3, and let me say multiply these events. Multiply that by different ways. So here, in this case, each of these is a choice. So this one is a choice, and this one is another choice, a different choice, and this one is a choice, and for this choice, there are that many different ways of accomplishing, making that choice. For this choice, there are that many different ways of making this choice, that many different ways of making this choice. So and that's all these three choices go into accomplishing the original task. So in how many ways then we can achieve the original task? By taking the product of these individual options or choices we have for accomplishing each choice. So different options of accomplishing each choice. Okay, so this is just a rough description of what the multiplication principle is. Like I say, it's everywhere in probability calculation. Extremely useful way of counting or figuring out the probability of events. So let's see some examples for this, of applying this principle. So suppose there are 14 items on a menu. Serving the customers, and the question is in how many different ways can the customers be served from this menu? Okay, so you can pick item number 7, and waiter number 1 might serve you, or waiter number 2, or waiter number 3. All of those are different ways of being served off of this menu at this restaurant. So how do we know how many total different ways are possible? So we have in this task of ordering and receiving your order has 2 choices. One is the number of items on the menu, So that's items on menu or on the menu. And of course, then waiters, right? The number of waiters. So this would be the number of waiters. Okay, so we know that there are 14 items on the menu, and we know that there are 3 waiters to serve customers. So multiplying them by the multiplication principle, and we get 42 different ways. There are these many possible ways of being served off of this menu with these waiters at this restaurant. Okay, so that's one example of application of the multiplication principle. Okay, let's do another example. So suppose, again, once I finish writing a problem down, you're welcome to, and I encourage you to pause the video, write down your own solution, and then compare it with mine after you go back to the rest of the video. So. Can he wear? Okay, so here we have pairs of shoes. So I'll just put the horizontal line to represent that choice. So here, or we can identify each choice by its what it is. So shoes, choosing shoes, and then socks, and then slacks, and then of course sweaters, right? And then, so we have, this guy has 3 pairs of shoes to choose from, and 8 pairs of socks, and 4 pairs of slacks, and 9 sweaters, right? So by the multiplication principle, we can multiply all of this, and the answer would be there are a total of 864 possible ways of dressing up using these clothing articles. Okay. Let's do another example. and repeated letters are not allowed. And the question is how many different alphanumeric codes are possible for this lock. Okay, so now it would be a good time for you to pause, write down your solution, and then compare it with mine after you come back to the video. Okay, supposing that you've come back and you have your own solution now, this combination lock has 5 settings. Okay, so let's draw 5 settings like that. The first 3, these are numeric. These are numeric ones, and these are alphabetical, the last 2, right? Okay, and it says for the numeric settings, these 3, any digit from 0 to 9 may be selected, and repeated numbers are allowed. This is pretty important information, right? So 0 to 9, how many digits we have from 0 to 9, including 0 to 9? 10. Right? So if this setting has 10 options for us to choose from, because there are that many numbers exist from 0 to 9, and repeated numbers are allowed, then how many numbers can we choose from for this spot? Again, 10, right? Because the repeated numbers are allowed. So another 10, and that doesn't exhaust or reduce the numbers of choices we have for this setting, because this is again a numeric setting. So again, we have 10 options for that. So if you pick 9 for this, for example, then you can pick 9 again here and again here. Okay, repeated numbers are allowed. That's the significance of that statement. It tells us how many options we have left to choose for each spot. So with alphabetical, and of course this is the English alphabet we are using, so the last 2 settings are alphabetical, and repeated letters are not allowed, right? So out of the 26 letters in the English alphabet, so if I pick A, so I have 26 options for this setting, right? 26. Once I pick that letter, whichever one it is out of the 26, we don't know, but whichever it is, I can't choose that letter for here, right? Because repeated letters are not allowed. So how many choices do I have here? 25. Okay, so now that's how we figure out how many options we have for each choice. And by the multiplication principle, you can multiply those, and we get 650,000 possible settings for this combination lock. Okay. By the way, just clarifying, combination itself is a calculation we get to later on in chapter 8. So this combination has nothing to do with that combination. This combination lock is just, as you know, it's how these locks are called. But this has nothing to do with that calculation which we will talk about when we get to chapter 8. So these examples wrap up our discussion for section 7.3. When we come back later, we will start talking about the topics in section 7.3. So for now, have a good day or have a good night, depending on where you are on the planet, and I'll see you next time.